Imagine plunging into the universe's absolute darkness. A black hole waits in the silent void of space. No light can escape its terrifying gravitational pull. But what actually happens to your physical body inside? The answer is far stranger than any science fiction movie. Let's begin the journey into the ultimate cosmic mystery. Our stickman astronaut volunteers for this one-way mission. He approaches a stellar mass black hole, about 10 suns heavy. From a distance, it looks like a hole in the stars. But this is no empty space, it is a shadow. We are looking at the event horizon, the point of no return. Anything crossing this invisible boundary is trapped forever. Even light, the fastest thing in the universe, cannot escape. Our astronaut starts his descent toward this ominous dark sphere. At first, nothing feels different or strange to him. He floats peacefully in the silence of his spacesuit, but an outside observer sees something completely different happening. This is the first bizarre effect of entering a black hole. Time itself begins to slow down near the event horizon. This phenomenon is known as gravitational time dilation. Einstein predicted this over 100 years ago. Gravity does not just pull on matter, it pulls on time. The stronger the gravity, the slower time moves forward. To the astronaut, everything feels normal and continuous. His watch ticks at the same regular speed as always. But to us watching from a safe distance, time stretches. His movements appear to slow down dramatically. He looks like he is moving through thick syrup. As he gets closer to the horizon, he slows even more. The light from his suit becomes harder to see. The light is struggling against the intense gravity to reach us. It loses energy and shifts to a longer wavelength. This effect is called gravitational redshift. Our astronaut's bright white suit turns a dim red. Then the red fades into invisible infrared darkness. We see him frozen at the edge of the black hole. He appears stuck there, preserved like a bug in amber. But from his perspective, he has already moved on. He crosses the event horizon without even noticing it. There is no sign, no barrier, no flash of light. He simply passes the point where the universe says goodbye. Now he is truly inside the black hole's domain. Everything changes the moment he crosses that invisible line. The future and the direction down become the same thing. In normal space, you can move in any direction freely. You can go left, right, up, or down as you please. Time flows forward, no matter where you are located. But inside a black hole, space and time swap roles. The direction toward the center becomes the inevitable future. You cannot stop moving toward the center, just like you cannot stop moving toward tomorrow. Avoiding the singularity is as impossible as avoiding next Tuesday. This is the terrifying reality of the black hole interior. All paths lead to the same destination, the center. But before he reaches the center, gravity attacks his body. This is the moment most people fear the most. It is called spaghettification, a real scientific term. Gravity pulls on his feet much harder than his head. This is because gravity gets stronger the closer you get. His feet are slightly closer to the center than his head. The difference in force creates a massive stretching sensation. His body is pulled into a long, thin strand, like spaghetti dough being stretched by a chef. His muscles, bones, and skin stretch beyond their limits. The pain would be unimaginable if he survived this long. But for this video, let's assume he has magic armor. He needs to survive to see what happens next. As he falls deeper, the view behind him changes dramatically. The universe outside shrinks into a bright circle of light. All the light that falls in gathers behind him. It looks like a circular window looking out at the stars. But this window gets smaller and smaller as he falls. It is his only connection to the rest of existence, and it is closing rapidly. Time dilation also affects what he sees looking out. As he falls, he sees the universe speed up. The future of the universe flashes before his eyes. Stars are born and die in mere seconds. Galaxies spin and collide like frantic dancers. He watches the entire history of the universe in fast forward. He might even see the black hole evaporate eventually. Yes, black holes can evaporate over immense timescales. This is called Hawking radiation, a slow process of leaking energy. But that takes trillions of years for a stellar black hole. Our astronaut falls toward the center in mere seconds. He approaches the singularity, the heart of the black hole. This is a point of infinite density and zero volume. All the mass of the dead star is crushed there. Our understanding of physics completely breaks down at this point. Quantum mechanics and general relativity contradict each other here. We do not truly know what happens at the singularity, but we have some very strange theories about it. Some scientists think all information is destroyed here. This violates the laws of quantum mechanics. Information, the state of particles, should never be lost. This is known as the black hole information paradox. It is one of the biggest puzzles in modern physics. Stephen Hawking bet that information was truly lost forever. But other physicists argued that the information must be preserved. Maybe it is stored on the surface of the event horizon, like a hologram containing all the information of a 3D object. This leads to the holographic principle theory. Our universe itself might be a hologram projected from a 2D surface. But back to our falling astronaut. His body is shredded into atoms at this point. His atoms are crushed into subatomic particles. His particles merge with the singularity's mass. He becomes part of the black hole's gravitational field. He is gone forever, or is he? Here is where the story takes a bizarre twist. Not all black holes are created equal. We looked at a stellar mass black hole, 10 times the sun, but there are supermassive black holes at galaxy centers. These monsters are billions of times heavier than our sun. The physics inside a supermassive black hole is different. The event horizon is much, much further away from the center. The gravity gradient is much gentler near the horizon. You could cross the event horizon without being spaghettified. You would not feel anything special when you cross. you would still be alive, at least for a while. This opens a door to even wilder theories. Some scientists think black holes could be wormholes. Passing through might take you to another universe. This is based on solutions to Einstein's field equations. But entering a wormhole is not an easy trip. The passage would likely collapse before you got through, unless the black hole was spinning and electrically charged. A rotating black hole is called a Kerr black hole. Inside, there might be a ring singularity, not a point. This could theoretically create a tunnel through space-time. This tunnel is called an Einstein-Rosen bridge. It connects two distant points in the universe. Or it might connect to a completely different universe entirely. This would be a white hole on the other side. A white hole is the opposite of a black hole. Nothing can enter a white hole, only leave it. It spits matter out instead of pulling it in. No white holes have ever been observed in space, but the math says they could theoretically exist. So our astronaut might not die after all. He might be spit out somewhere else in the cosmos, or he might emerge in a different universe entirely. Time would also work very differently for him. He could arrive in the distant past or far future. He might even meet himself falling in. This causes all sorts of time travel paradoxes. The universe might have rules to prevent this. We simply do not know for sure yet. Let's step back and look at the bigger picture. Black holes are not just cosmic garbage compactors. They play a crucial role in galaxy formation. The supermassive black hole at our galaxy's center holds us together. It is called Sagittarius A star, and it is massive. Without it, our solar system might not exist. We literally owe our existence to a black hole. Scientists recently photographed a black hole for the first time. The Event Horizon Telescope captured the image in 2019. It showed a glowing orange ring around a dark shadow. It looked exactly like Einstein's equations predicted, a perfect confirmation of general relativity. We are also detecting black holes colliding. LIGO detects ripples in space-time from these collisions. These gravitational waves travel across the universe to us. They tell us about the most violent events in history. So what is the final answer to our question? What actually happens to your body inside a black hole? For a small black hole, you are spaghettified and destroyed. For a supermassive one, you might survive longer. You might even travel to another universe, but you can never come back to tell us about it. The universe keeps its secrets locked behind the event horizon. It is a one-way trip into the ultimate unknown. And that mystery is what makes black holes so fascinating. They challenge everything we think we know about reality. Space, time, matter, and energy all break down. Yet they are real, observable parts of our universe. The next time you look at the night sky, wonder. Somewhere out there, a black hole waits in the dark. Thanks for watching this deep dive into the cosmos. What would you do if you could visit a black hole? Let us know your theories in the comments below. And don't forget to subscribe for more mind-bending science. Stay curious and keep looking up at the stars.